A review of our robot design shows we have a single motor which has been using to drive the small gear onto the larger gear, raise the arm, and our scoop bucket at the front. What we want to find out is a single motor good enough to do that. And to do that, we have to calculate the torque. I started out by creating a much simpler version of my robot. We don't need all of the detail. I don't even need the gears, but I've left them in just to show you what it looks like. Here's the arm. I've replaced the bucket, and there's a point where I'm going to be placing a load at that point. For the gears, I've created a constraint called align gears. If we move the gears, they may not be perfectly aligned, so I've set them up properly using work planes. I have to turn that off so it can move. I'm going to add a second constraint, and that's a motion constraint. Change the solution, and select two circular surfaces, one on the small gear and then on the larger gear. I know there are a 12 tooth and an 84 tooth gear. 1 to 7 is the ratio. Now with that in place, we can see that the small gear will rotate 7 times, while the larger gear will rotate only once. I'm going to put that back into position, a little almost horizontal. And with that in place, I can now go over into dynamic simulation. That's an environment. There are a number of them, such as dynamic simulation, stress analysis, and frame analysis. Let's go into dynamic simulation. We can see the simulation player, and you'll also notice that the browser is a little bit different. Because of the default settings, any assembly constraints are converted to standard joints. And we'll have a look at the types in just a moment. In the browser, the software has decided that certain parts are grounded. That makes sense, as you can see. We also have mobile groups. These are parts that can move, such as the small 12-tooth gear. We have the standard joints. These were axial constraints converted to revolution joints. And we'll be adding the loads. In the simulation player, that's what we'll do when we get all our settings in place. Now let's insert a joint. And that's going to be between the gears. You can see all the categories, slightly different names, so if you need help, just click on that icon. These are the major categories, and here are the subcategories. I'm looking for rolling cylinder on cylinder. Now that's between the pitch circle of the gears. Now I've created an extruded surface to show you that just a little bit better. You need to create these to create the rolling cylinder on cylinder joint. Now it's telling me that my assembly is over-constrained by 1 degree. That's because I have that rolling cylinder on cylinder, and I also had the motion constraint, and you can see that. It will go away with a couple of other settings. I go into the rolling joints, and then go to the properties, then into the parameters. I looked at the specifications on the VEX website, and it tells me the gear is 20-degree pressure angle. So I'll fill that in. Now I can start to look at the loads. Gravity by default is not defined, so I need to take the suppression check mark off. You can see the indication as to gravity. Downwards, that's good. And I want to add the second force. The location is that point that I had created. Direction will be a vertical edge. And the magnitude, I'm going to make that 2 pounds. And there we go. So let's run the simulation. Well, that's not very good. Obviously we've got a little more work to do. And in the next lesson, I'll show you how to add the parameters to resolve that issue.